Here we are in chapter 9, and we're going to talk briefly about vectors. We're going to start with vectors in 2 dimensions in the xy plane, and then the next section we'll just go on into 3 dimensions in the xyz R3 space. So you've probably used some vectors in some of your basic engineering courses or in your introductory physics courses. A vector is just something that we use to represent magnitude and direction. For example, wind, the direction that the wind travels, and how much magnitude or what miles per hour the wind is moving. You'll see that on a weather map. The big long arrows mean there's going to be a real harsh wind if it's a light wind, and then you have a nice short arrow, and from the direction the wind is originating toward where it's heading. So that's where maybe you've seen some vectors. So we represent vectors by little arrows with an initial point and a terminal point. So the direction is clear, and then how long the vector is gives its magnitude. I've drawn a vector from point 1, 3. Here's point 1, 3. In R2 to the terminal point 5, 8, so over 5 up 8. So the vector from 1, 3 to 5, 8 would look like that. And we can write that vector by taking the components or the coordinates of the terminal point and subtract off the coordinates of the initial point, and those will give you the components of the vector, the x component in the x direction and in the y direction. So we can represent this vector from point P to Q. Maybe we can call it vector PQ, where we write the initial point first and the terminal point second. Here I've just named it vector V because I referred to it later on. From point P to point Q, so that's how we write it with the arrow pointing toward the terminal point. We can also draw what's called a vector in standard position that corresponds to this. So what we would do for that one is we would just start at the origin and go to the right 4 and up 5. So to the right 4 and then up 5, that's 3, 4, 5. And so here's that vector in standard position. It would be parallel to the vector from 1, 3 to 5, 8, but it would have its initial point at the origin. That's called a vector in standard position. The magnitude, sometimes called the norm of the vector, is just its length. And we can find that by using the Pythagorean theorem. For instance, let me draw that vector again. So we're going to go from 1, 3. Put some coordinate axes down here. So we'll go from 1, 3. Oh, I'm not going to be able to get all the way up to 8. Let's make that 1, 3 to 5, 8. So that's 3, 4, 5, 6, 7, 8. So the magnitude of this vector is its length, but we've had enough right triangle trigonometry that we can find its length by using the Pythagorean theorem. So if I went from x is 1 to x is 5, then this length is 5 minus 1, or 4. And then if I go from 3 to 8, then from 3 to 8, the length of that is 5. And so the magnitude of this vector, which I said we denoted like this, the magnitude of vector V is the square root of the sum of the squares of the lengths. So it's 16 plus 25 here under the square root sign, which I think might be square root of 41. So in general, the magnitude of a vector, the magnitude of a vector, if I just write the vector V with components A, B, then its magnitude will be the square root of the components squared added together. So again, that's just the Pythagorean theorem. When we talk about vectors and numbers associated with vectors, we call that the numbers scalars. Scalar's just some regular old number. If we take a scalar and multiply a vector by a scalar, you do that component-wise. Some number times the vector AB is that number times component A, and then that number times component B. So for instance, if I took 3 times the vector 4, 5, I get the vector 12, 15. So if this was the vector 4, 5, 3 times that is a vector that's 3 times its length. If I multiply a vector by a negative number, I change the direction. So the vector minus AB, if this is vector vector AB, then minus AB goes in the opposite direction. So what I'm saying is that if you multiply by a scalar, it just, like in this example, triples the length. So let's compute the length of the vector 12, 5, which we got by multiplying vector 4, 5 by 3, and show that they have 3 times the length. So the norm of vector whose components are 12 and 15 would be the square root of 12 squared plus 15 squared. 12 squared is 144. 15 squared, is that 225? Oh, let's give it a shot. Yep, it's 225. And so when I add those together, I get a vector whose length is 369. Let's see, so my guess is that there's a factor of 9 in there. So 9 goes into 36 4 times. 9 goes into 9 one time. And there it is. Square root of 9 is 3. Square root of 41 is what we got earlier on as the length of vector 4, 5. So multiplying by a scalar, if the scalar is positive, keeps the vector in the same direction and just makes it that much longer, or if the scalar is between 0 and 1, it'll make it shorter, it'll contract the vector. But if it's negative, it turns the vector around. A unit vector is said to be a vector of length 1. So here's an example of a unit vector, and I'll show you that it's a unit vector by computing its norm. But you probably know that it's a length 1 because you've seen this ordered pair in trigonometry. Square root of 3 over 2 squared plus 1/2 squared, and then we take the square root of it. So that gives us the square root of 3/4 plus 1/4. That's the square root of 1, which is indeed 1. We can always find a unit vector in the same direction as a given vector just by taking the given vector and multiplying by the scalar that is the reciprocal of its length. In other words, we know that the magnitude of vector 4, 5 we found earlier was the square root of 41. So if I take this vector and scale its components down, I have a unit vector that has the same direction. If I wanted a unit vector in the opposite direction, I multiply by the negative reciprocal of the length. And now I can find a vector that has the same direction and maybe a length of 8. So a vector in the same direction with a length of 8. I've got my vector scaled down to a length of 1. Well, let's just take it and multiply it by 8. So I multiply each component, and I get 32 over the square root of 41 and 40 over the square root of 41. And that vector now has a length of 8, and I didn't change the direction since I multiplied by a positive number. So in general, a unit vector in the same direction as the vector AB. If I take it and divide by the magnitude, which I would write as 1 over the magnitude of V multiplied with V. That's a unit vector in the same direction as V. Once you get something of length 1, you can make it any other length by multiplying by whatever size scalar we're talking about. And the nice thing about vectors is you add them the way you think you should. You add component-wise. So if you had a vector whose components were AB and another one whose components were CD, and you add them, then it's just A plus C, and then B plus D is the other component. Subtraction, you just subtract component-wise. So for instance, if I have the vector 4, 2, and I subtract the vector 1, 5, I get the vector 4 minus 1 is 3, 2 minus 5 is negative 3. Geometrically, the addition of two vectors is a vector that will look like the diagonal of the parallelogram that I can draw, trying to draw these as parallel to one another. This vector here is vector V plus W. Now if I subtract two vectors, I can represent that as well. Keep in mind that V plus W is V plus minus W, V minus W is V plus minus W. So here's V and W, so minus W flips in the other direction, but with the same length. And so if I make my parallelogram over here, then V plus minus W could be right here. But typically what we do is we pick that arrow up and we take this point over to here and the head right there, and I get a vector that's parallel with the same length and the same direction, and that's vector V minus W. You'll use that kind of thing in physics. If V and W represented forces acting on an object right here, forces in a certain direction with a certain magnitude, then that object would move from here to here. And the same kind of deal with the subtraction. If I've got a push in one direction and a pull in another, and I look at the resultant vector, then that would look like the vector V minus W. So it's kind of easy stuff. We'll do the same thing in 3 dimensions. We still have scalar multiplication. We have a 3-dimensional version of magnitude where we just put a third component squared under the radical sign. So everything is going to be kind of easy schmeezy right here in Chapter 9, but relatively important because most of Calculus 3